we're gonna take a look at joining processes, and we're gonna start with fusion welding process. So in this chapter, we're gonna learn about fusion welding. It means that two pieces are joined together by heat, and which melts and fuses the interface. This sometimes uses a filler metal. Different type of fusion welding processes will be described in this chapter. We will begin with oxygen gas welding. Then we will look at arc welding, in which the electrical energy is used with consumable and non-consumable electrodes. And we will conclude the chapter with welding with high energy beams such as electron beams and lasers, which are used as basically heat sources. So if we look at in general what the joining processes are, so we know all products are assembled from individual parts, so we need to join them, and therefore joining techniques are important to understand. And there are several ways to join parts. One is welding, other one is brazing, soldering, and adhesive bonding, and mechanical fastening. And if we want to divide them into categories, we can divide them into three categories, which we will learn one by one. First, we will start with welding in this chapter. Then there is adhesive bonding, and then mechanical fastening. When it comes to welding, we classify welding into three categories. Fusion welding, which we learn in this chapter. Then we will learn solid state welding, and then brazing and soldering we will learn lastly. What is fusion welding? So this is melting together and coalescing of materials by means of heat. The heat supply can be chemical or electrical. Filler metals can be used or may not be used. So filler materials are where we add it to the weld area to connect the materials, to join the materials. If we don't use filler materials in the welds, then it is called autogenous welds. And so fusion welding composed of use of consumable and non-consumable electrode arc welding and high energy beam welding. And as we weld the materials, of course, the welded joint undergoes a major structural changes. Therefore, that joint will have different properties, and it will affect the performance of the materials. So we will not go through those changes, what type of structural changes are happening in the material, but we will learn about different techniques, and your book covers all these informations if you guys are interested. Maybe we'll just learn what type of techniques we have and what are their characteristics. So oxy-fuel gas welding refers to a group of welding processes that use the flame produced by the combustion of a fuel gas and oxygen as the source of heat. This technique have largely been replaced, but the process is still popular in terms of for small scale and repair operations, because it can weld most ferrous and non-ferrous metals. It's portable and low capital investment required. So common fuel is acetylene, which is C2H2. The temperatures can go up to like 3300 degrees C. In the first, so there is two-stage reaction. In the first stage, supplied oxygen and acetylene react to produce carbon monoxide and hydrogen, as you see in the first stage. And this reaction occurs near the tip of the torch and generate intense heat. The second stage of the reaction involves the combustion of the carbon monoxide and hydrogen, and occurs just beyond the first combustion zone, and you can see the second reaction right there. So these two-stage combustion process produces a flame having two distinct regions, a light blue inner cone and a darker blue outer cone. Three different types of flames can be obtained, basically by just varying the oxygen to acetylene ratio or oxygen to fuel gas ratio. If the ratio is 1:1, the flame is neutral. Most welding is done with a neutral flame because it will have the least chemical effect on the heated metal. There are higher ratios, like with a higher oxygen supply. That's what we call oxidizing flame, which is hotter than the neutral flame, similar in appearance. Such flames are used in welding of copper and copper alloys. This is because in those alloys, a thin protective layer of oxides forms over the molten metal. But in welding of steel, for example, with this flame, it is considered harmful because excess oxygen reacts with carbon in the steel, which lower the carbon content in the region around the weld. So when you have, instead of higher oxygen, if you have higher of the fuel, when the oxygen is insufficient, the flame is called reducing or carburizing flame. In this case, the flame temperature is not as great, meaning it doesn't go up to very high temperatures. It is lower. But the flames are characterized by 3 flame zones. Okay, we're gonna see. This is, as I said, then suitable for applications requiring lower heat, such as brazing and soldering, etc. So now we have described there is inner core and you see in a neutral flame. This is due to having two different reactions taking place, and you can see that inner core in the flame, both in neutral and oxidizing flame. In addition to that, the carburizing flame has forming acetylene feather. Due to this excess of fuel, we have three zones, remember, in the carburizing flame. And so in the image D, we are seeing the principle of oxy-fuel gas welding process. We see the gas mixture is introduced through the welding torch, and there is the flame here, and this is your base metal, and you have a filler rod which is melting and filling the part, and this region is already solidified. Well, then there is this region that is the molten metal. Filler metals, there can be a slight gap exist between the pieces being joined. Therefore, a filler metal can be added in the form of a solid metal wire or rod. To promote the formation of a better bond, fluxes can be used, as you see here. So the flux can be used with as a coating to these filler metals, or they can be added as a powder. So the flux, what does flux do? It basically remove contaminating oxide. In addition, it forms a gaseous shield produced by vaporizing flux. Can prevent further oxidation during the welding process, which are all helpful, basically making the joint more stronger, forming a better bond between the joining surfaces. As we have said, this technique can be used with most ferrous and non-ferrous metals for almost any workpiece thickness. And here you see the practice where in image A we are seeing the torch, and image B we are seeing within the torch there is oxygen flowing from here and acetylene flowing from here, and they combine here in the mixing chamber, and these are attached to the acetylene gas and oxygen gas tanks. Here is this torch here, which is attached to with the hoses to the gases. Basically, this is the basic equipment we use in oxygen gas welding. This is basically a simple process, versatile, portable, economical. Pressure gas welding, it's a process that uses equipment similar to oxy-fuel gas process to produce butt joints, basically joining the ends of objects such as pipes, railroad rail. So the ends are heated with a gas flame to a temperature below the melting point, and the soft metal is then forced together, as you see in the image, under pressure. can be actually a form of solid state welding, where the gas flame basically softens the metal, and basically two parts are coalesce by pressure, as you see, and then there is this flash forming, you can see right there, and then this can be trimmed off later. Now let's look at, so we have seen oxy-fuel gas welding, and now we're gonna see arc welding process. In this case, the heat required comes from electrical energy. So in the case of non-consumable electrode, as the name implies here, we use a non-consumable electrode, like in this case it is tungsten electrode. So here basically the electrode is not consumed by the arc. And an alternating current AC or direct current DC power supply produces an arc between the tip of the electrode and the workpiece to be welded, and temperatures are very high, goes up to 30,000 degrees C. You see it is higher than those developed in oxy-fuel gas welding. Each process and application, however, requires the selection and specification of the welding voltage, welding current, arc polarity, meaning the direction of current flow, like is it AC, DC, welding speed, arc atmosphere, electrode and filler material, flux. So all will depend on like what type of electrode you have, the metals, what type of metals you try to weld, etc. Here we see the effect of polarity and the current on the type of weld. So when we say straight polarity, we see it in image A. In this case, the workpiece is positive. It is anode, and the electrode is gonna be negative. It's gonna be the cathode. And this type of straight polarity produces a narrow and deep welds like this one. And in reverse polarity, where the workpiece is negative, and here like this one, workpiece is negative, and then the electrode is positive, then the weld penetration is less, and then the weld zone is shallow and wider, as you can see here. Okay. So alternating current means this positive and negative charge it's changing. So workpiece is, for a second it's negative, then positive, negative, it's positive. Please also watch the videos, right? I'm sending. It also describes this process there. And that is the alternating current, as you see in the image C. Weld shape is somewhere in between straight and reverse polarities of direct currents. Gas, so one example of non-consumable electrode arc welding is gas tungsten arc welding, or known also as tungsten inert gas welding. So in this case, a non-consumable tungsten electrode provides the arc but not the filler metal. So the filler metals are used, and these are similar to the metals that to be welded. And in inert gas, it can be argon, helium, flows through the electrode holder to provide a protective shield around the electrode, the arc, and the pool of the molten metal, and just around the heated areas. This technique is expensive, but it produces very high quality welds. In this technique, no flux is employed, and most common engineering metals and alloys that can be welded by this process are, because there is an inert gas, it makes it particularly attractive for reactive metals like aluminum, magnesium, titanium, as well as some superalloys, refractory metals. In this figure, we are seeing this process and the general setup. Here you see we have tungsten electrode here, and then the gases are flowing through the electrode holder here. You see these are attached to the inert gas supply, and there is the filler wire, and you see the shielding gas is forming, and that's it. And then there is plasma arc welding. And in this case, the arc is maintained between a non-consumable electrode and the workpiece. In this case, the non-consumable tungsten electrode is set back within the torch in a way as to force the arc to pass through or be contained within a small diameter nozzle. An inert gas is forced through this constricted arc, where it is basically heated to a high temperature and forms a hot, fast-moving plasma. And plasma is basically an ionized gas consisting of equal numbers of electrons and ions. The emerging stream of this ionized gas then transfers its heat to the workpiece and melts the metal. There are two methods of plasma arc welding. One is transferred arc and the other is non-transferred arc. In transferred arc, the arc transfers from the electrode to the workpiece. Here you see it is transferred from the electrode to the workpiece. And there is non-transferred arc. In this case, the arc is in between electrode and the nozzle, and the heat is carried to the workpiece by plasma gas. So it is in between the workpiece. It's in between the nozzle and the electrode here, and this one is in between the workpiece and the electrode, and this one is transferred by the gas. Here you can see to the workpiece. So that's the difference. In atomic hydrogen welding, the arc is generated between two tungsten electrodes with a shielding atmosphere of hydrogen gas. So what happens, the gas is normally diatomic, meaning H2. However, when temperatures are over 60,000 degrees C near the arc, the hydrogen breaks down into its atomic form. This absorbs a large amount of heat from the arc. And then when the gas strikes to the cold surface of the workpieces that is going to be joined, it recombines into its diatomic form, H2 again. This rapidly releases the energy, the heat, which makes the temperatures go up to 4,000 degrees C. And therefore this heat is used to join the parts. And this is one of the few joining techniques that can be used for welding of tungsten. Now let's take a look at consumable electrode arc welding. In this case, the electrode is consumed and they become the part of the weld. And the first example is shielded metal arc welding. In this case, again, you have an electrode and there is electric arc generated between the electrode and the workpiece. This heat melts the electrode and there is a coating on the electrode, which is, remember, the flux is sometimes coated on the electrode. So electrode is coated with the flux. And this coating melts, and electrode tip melts, and it also melts the base metal. So this mixture becomes the weld when it solidifies. So the coating, the flux, deoxidizes weld area and provides a shielding gas. You can control the composition of the flux. So in this case, the flux acts as to deoxidize and to remove the impurities from the molten metal. And then usually this technique is used in construction, shipbuilding, and pipelines. And here is the illustration of this process. But the videos are better, you can actually see the process. So watch those. Here you see the electrode and a device that controls the current, AC, DC, and we have the workpiece and the arc is forming, and you see in here there is the coating on the electrode. This coating melts together with the electrode and forms a shielding gas. There is protective slag coating that is forming on top of the molten metal. This accumulate impurities, prevent oxidation, and it also slows the cooling of the weld. Another example to consumable electrode arc welding processes is submerged arc welding, and in this case no shielding gas is used. Instead a layer of granular flux is deposited and that is used as the shield. This flux is made of like lime, silica, manganese oxide, calcium fluoride, and other compounds. And this flux is fed into the weld zone from a hopper by gravity flow through a nozzle, and you can see the shape of that here. I'm sorry, this is the This is the flux hopper here, this one, so not that one. Let's erase that. Okay, so this is where we feed the flux. As you see, it is fed to the process. And you can also see that this thick layer of flux completely covers the molten metal. This prevents spatter, sparks, and suppresses the intense ultraviolet radiation and fumes characteristics of this process. The arc is maintained beneath the blanket of this flux layer. Only small amount of smoke or flames being visible. If you watch the video, you're gonna see. So a portion of this flux melts and acts to remove impurities from the molten metal. And unmelted flux is recovered by a vacuum system and is reused. This flux layer also provides thermal insulation to the weld, and this causes slow cooling, which produces soft and ductile welds. But this process is limited mostly to welds in a flat or horizontal position. So in gas metal arc welding process, the weld area is shielded by inert gas like argon, helium, carbon dioxide, or other gas mixtures. Here you have a consumable wire, bare wire, that is automatically fed through the nozzle. It is kept feeding to the system, basically through a nozzle into the weld arc. Since there is the inert gases, we don't need flux. So this metal wire becomes the consumable electrode, and the arc is maintained between the workpiece and this wire electrode, and this of course continues to provide the necessary filler metal. This technique can be applied to all metals, like steels, aluminum alloys, magnesium alloys, copper, and nickel. These are the most common ones. Here you see the shielding gases are being fed together with the electrode that is keep becoming a part of the weld. Here you see the base metal, molten metal, and shielding gas around the weld, and this is the system that controls all the power and the gas that is coming into this gun, basically this part, right? So another example is flux core arc welding. This is similar to gas metal arc welding. In this case, the electrode is tubular and, as the name implies, filled with flux. Therefore, the term flux core comes from. So when the arc is established, the vaporizing flux again produces a protective atmosphere, and molten material forms therefore in isolating slag layer over the weld pool. Of course, this slag will require subsequent removal. The continuous electrode is fed automatically through a welding gun, with the electrical contact being maintained through the bare metal exterior of the wire near the exit of the gun. Such cord electrodes produce a more stable arc, improve the weld contour, and produce better mechanical properties of the joint. This technique is used for welding various types of joints, mainly steels, stainless steels, and nickel alloys. Compared to gas metal arc welding process, this one has higher deposition rate. Therefore, this has led it to its use in joining a section with various thicknesses. The advantage here, various weld metal chemistries can be developed and obtained by just adding various alloying elements to the flux core. So here is the illustration of flux core arc welding process, and there is the tubular wire, and at the core it has an inner core that is filled with flux. And with the flux, the slag, you can see the slag forms, and to remove the oxides and other impurities from the molten metal. And there is electrogas welding. This is used primarily for welding the edges of parts vertically in one pass, with the parts placed edge to edge. The weld metal is deposited into a weld cavity between the two parts to be joined. So it's basically similar. It's a continuous vertical position arc welding process where there is the arc between the electrode and the workpiece. You see these are the weld metal here. And there's shielding gas, and there is the welding wire, welding gun. Similar process is electroslag welding. In this case, the main difference is the arc is initiated between the electrode tip and the bottom of the part to be welded. Flux is added, which melts by the heat of the arc, and then the slag forms, and the molten slag reaches to the tip of the electrode, and the arc is extinguished. heat is produced then continuously by the electrical resistance of the molten slag. So because here the arc is extinguished, we cannot classify this technique strictly an arc welding process. So electrodes for consumable arc welding processes are classified according to the following properties: strength of the deposited weld metal, and current AC or DC, and type of coating. So if you check your book, your table 30.3, just giving you a general information that you might need in the future, is you're gonna see electrodes are identified by numbers and letters, and it will have information about the strength of the weld metal. It will have information, these numbering, their designations will have information about what type of current is going to be used, etc. So all these informations will be included in the designations of the electrodes. So we talked about electrodes are being coated with materials, and what is the purpose of these coatings. So there are several functions. One is to stabilize the arc and then generate gases to act as a shield against the surrounding atmosphere, control the rate at which electrode melts, act as a flux, and flux is to protect the weld against the formation of oxides, nitrides, and other inclusions, which results in the formation of slag, and slag protects the molten weld pool. And it also can add alloying elements. As we talked, this can enhance the properties of the joint. There's another category beside oxy-fuel gas welding. We learned about arc welding with consumable and non-consumable electrode. And now we take a look at high energy beams like electron beam welding. In this case, again, the heat somehow needs to be generated. In this case, it is generated by high velocity narrow beam electrons, and the kinetic energy of the electrons is converted into heat as they strike the workpiece to be welded. But this will require special equipment in order to focus the beam on the workpiece, and typically in a vacuum, because if you don't have vacuum, you cannot concentrate this electron beam on the workpiece. Almost any metal can be welded with this technique. No shielding, because there is vacuum, right? So there is no need for shielding gas, flux. And of course, this will create good quality welds, high purity. In laser beam welding, this technique utilizes a high power laser beam as the heat source to produce a fusion weld. It is focused onto a very small area. The beam has high energy density and deep penetrating capability. This beam can be directed, shaped, and focused precisely. This technique has become very widespread and is now used by most industries. It has a good quality, good strength, and generally welds are ductile and free of porosity. Typical metals and alloys welded with this technique include aluminum, titanium, ferrous metals, copper, superalloys, and refractory metals. Because of the nature of the process, this technique can be done in otherwise inaccessible locations, but the safety is important because the lasers are dangerous. Laser beam dangerous to the eyes and skin. So in this image there is the comparison of the electron beam weld and gas tungsten arc welding, and you see that these techniques, like high energy beam techniques, they are suitable particularly for welding deep and narrow joints if you compare it to the gas tungsten arc welding. So we have learned oxy-fuel gas, arc, and high energy beam welding techniques, and at the end we need to generate heat, and this can be like converting electric energy to heat or chemical energy to heat, or using high energy beam to generate the heat. At the end, heat is used to join two parts together. Shielding gases are used to protect the weld area against oxidation. Filler metals may or may not be used.